Question 4. Figure 3 shows some reactions of aqueous ions. What have I got here? I've got iron 2, iron 3, hexaaqua iron 3 here. It's going to form precipitate J. Well, sodium carbonate produces hydroxide ions, so it's going to replace some of these waters with hydroxide ions. Carbonate ions with water makes carbon dioxide and hydroxide ions, so it's going to replace some of these waters, react with some of these waters and turn them into hydroxide ions. Now if it's making a precipitate, the overall charge is 0, so the overall charge has got to be 0. So I've got Fe with a 3 plus, waters with 0 charge at all, so I've got to balance out this Fe3 plus by having 3 OH minuses, so it will form FeOH3 H2O3, so 3 plus on the iron, 3 lots of 1 minus on the hydroxide ions, leaves no charge, waters have no charge, and that's going to be a brown precipitate. So that's just something that you've got to learn as a brown precipitate. Now this is quite a hard equation then to balance. We know that we've got FeH2O3 plus, and we know it's formed FeOH3H2O. We know we've got some carbonate ions. We know we're making carbon dioxide. It's reacting with some of the waters out of here, and it's making some hydroxide ions which are going into here. So this part isn't too bad, but then we've got a problem in that we've got to balance it still. We've got 6 waters here. We know that 3 of the waters are retained as ligands, and 3 of them are then released as waters. So we need a 3 here. Now then, if we have a look here, we've got 6 lots of H2O here, 6 waters on the left, 3 and 3 is 6 waters. So these OH3 OH minuses need to be balanced. So they've got to come from more of these waters in here. So more of the waters are being converted into OH3s as well. So I'm going to need a 2 in front of here. I'm going to need more of these to get the OHs balanced here. If I've got 2 lots of this, I've got 2 Fe's here, I'm going to need 2 Fe's here. Now I've got to balance the CO3 2 minus, the carbonate ion and the carbon dioxide. Well, let's have a look at this. How many oxygens have I got in this complex? I've got 6 times 2 is 12. In this complex here, I've got 3 and another 3 is 6 times 2 is 12. So the same number of oxygens in this complex is the same number of oxygens in this complex. But here I've got 3 H2O, I've got 3 O's. So I've got 3 extra O's on the right hand side. So the carbonate ion going to CO2 must create these O's on the right hand side. I've got 3 O's on the right hand side that don't appear on the left. Every time I turn a carbonate ion into a CO2, one of these O's become 2 O's, so I get an extra O onto the left hand side, so I'm going to need 3 each of those to balance up the oxygens. Give the formula of L and the equation for reaction 2. Concentrated HCl, so this provides Cl chloroligands here, but the Cl ligands, the chloroligands, are bigger than the water ligands, and you can only fit 4 around, so it's going to be FeCl4. We've got to work out what charge it's going to be. Well, Fe is still 3 plus, a chloroligand is a minus, so I've got a 3 plus and 4 1 minuses, so that's going to leave 1 minus left over. 3 plus, 4 1 minus, leaves 1 minus left over. The equation is easier. FeH2O3 plus, 4 Cl minuses, makes FeCl4 minus, and the waters are replaced by the 4 Cl ligands. Suggest a reagent for reaction 3. I need something that's going to reduce this, so I need a reducing agent, and zinc in sulfuric acid, excess zinc, plenty of zinc, zinc in sulfuric acid will reduce a transition metal. Give the formula of the precipitate M and state its colour. Well, M, so I've got ammonia. So ammonia, again, a bit like carbonate ions, will produce OH minuses. It's basic. It will produce OH minuses, and these will get replaced. Now, if it's a precipitate, it's got no charge. Fe has got 2 plus because the waters have got no charge. So Fe2 plus means I've got 2 OH minus ions. So Fe2 plus OH minus, two of them will create no overall charge. Waters have got no overall charge, and that's going to be a precipitate. It's a green precipitate. Transition metals have different shapes and many show isomerism. Give the different shapes of complexes and show how they lead to types of isomerism. Use examples of complexes of cobalt and platinum. Draw structures of the examples chosen. 6 marks. So what I've got to do is I've got to draw 3 different shapes of complexes and then explain how the 3 different shapes can lead to isomerism for the 6 marks. So I've got 1, 2, 3 marks here, and when I do the isomerism I'm going to get another 3 marks. So cobalt H2O6 with a 2+ charge, hexaaqua cobalt 2, can form 6 ligands. It's going to be an octahedral shape with a coordination number of 6 ligands around it. Cobalt, if I have my COCl4 as an example, 4 1- ions, cobalt is 2+, so it's 2- overall, coordination number equals 4, shape is tetrahedral. And then I've drawn a cisplatin as well as a different shape. Platinum has got 2 lone pairs up and down, and then it pushes the 4 ligands, the 2 Cls and the 2 NH3s. You should know about cisplatin being able to combat cancer as an anti-cancer drug. And cisplatin means that the 2 Cls are close to each other, next to each other, not opposite from each other, and the 2 NH3s are next to each other. Transplatin is where it's opposite. And this, because the 2 lone pairs are up and down, pushes the 4 ligands into a square planar shape. 4 ligands, coordination number 4. That gets me my 3 marks. And now I need to talk about potentially about the different types of isomerism in each of these. Okay, so cisplatin and transplatin. Cisplatin and transplatin, I've got the 2 Cls next to each other in cisplatin, and I've drawn them opposite each other for transplatin. So platin can be cis or trans in a square planar shape with the ligands either together, the same ligands together, 2 Cls together, and or opposite in trans. That's a geometrical isomer. So a geometrical isomer where I've got cis and trans, also known as Z on the same side as each other, or trans being E. So I've got Z and E, or cis and trans. I could do the same with cobalt, so I could have cobalt COH2O4OH2, so 4 water ligands and 2 hydroxy ligands. So, and then I could have the 2 hydroxy ligands next to each other as they are here in the plane, or opposite in the plane, and that's going to get you an extra mark as well. So by showing that I can have geometrical isomers in a square planar or an octahedral shape. Next here, I could have a bidentate ligand, so ethane dioate or 1,2-aminoethane could be a bidentate ligand. That's where a ligand forms 2 coordinate bonds. So I've got 1, 2, 3 ligands, still coordination number 6, but I've got 3 ligands, each with 2 coordinate bonds. And you can see here, if this is a ligand that's joined with covalent bonds, and then I've got 2 coordinate bonds in blue, then the ligand can be like this, and then another ligand, bidentate ligand, can be here and here, and then I can just join them up as a mirror image. So that's an example of a mirror image where I've got optical isomerism. M just represents any of the transition metals.